The objectives for today are that by the end of class you'll be able to explain Heisenberg's uncertainty principle. So you'll be able to tell me what it is and you'll be able to explain to me what it means and why it exists. Okay? Then you'll be able to describe how orbitals in the quantum theory are different from the orbits in Bohr's model. So we've seen Bohr's model, we understand what his orbits look like. Today we're going to look at the quantum model and orbitals. You're going to be comparing them, saying how are they similar, how are they different. And then lastly, you'll be able to describe for me what each of the quantum numbers means, what it tells you about an orbital or an electron. All right, let's just launch right in. So, scientists had this Bohr model, and they knew it worked for hydrogen, but it didn't work for anything else. Anything other than an atom that had one electron, the model kind of fell apart. So they started looking at things and trying to figure out why and what a new model should look like that would work for other atoms. They discovered, while they were doing this, that light, we know, behaves as a particle and a wave. Well, they discovered that particles, electrons, could also sometimes behave like waves. The theory was proposed by the French scientist Louis, and I'm going to mess up his last name. I believe it's de Broglie, something like that. I'm not great with French. But he was a French scientist, and he proposed this theory. There were experiments that were done that showed that electrons were able to be diffracted. Diffracting means bent. So if you ever passed light through a substance, you will notice that it bends. This is why if you put a pencil in a cup of water, the pencil looks like it's broken, like it's not lining up where the water meets. And that's because as light moves out of the air and into the water, it bends. Okay? Same can be true of electrons. They can be bent. And then also, they are able to interfere with each other. Okay? So light waves can interfere with each other. And we're going to do a little lab to observe that. So this lab is on page 106 of your books, and we're going to do it, and then we're going to come back together and answer some questions about it. What you should have seen, in case you didn't get a good grasp of it, was something similar to this, okay, where we have bands of light and dark, okay? So what's happening here is interference. Okay. Did you observe these interferences on the screen?
Yes.
Okay. So, the question then is, what does that tell you about the nature of light? The fact that interference can happen just indicates that light is acting as a wave here, because interference is a property of waves. So what's happening is you're getting, we'll use an example of a water wave because that's easy to see it in, okay? So in a water wave, you have a crest and a trough, right? Areas where water is being moved up and then where it goes down, and then in between is where it returns to sort of its baseline, okay? So imagine this water wave runs into another water wave, but this water wave lines up like this, okay? If they're of equal strength, what's going to happen to the water? Yeah, it's going to go flat, right? You're going to wind up with a wave that looks like that, if those two waves are of equal strength. If, let's say, this bottom wave was much, much stronger, so it had much deeper crests and troughs, okay, what you'd wind up with was a wave that was like littler, right? So they can cancel each other out. So when you're seeing those bands of it's light here, it's dark here, it's light here, it's dark here, what you're seeing is light waves running into each other and either making each other stronger or canceling each other out. So you get bands of areas where the light cancels itself out, and so you get those dim bands, and then areas where they're not interfering, then you still have light. scientists did some experiments and they discovered that the same thing can happen with electrons, which means if electrons can interfere with each other like that, then they must be able to behave like a wave, because this is a property of waves. Okay? So now that we know that electrons can behave like waves, we can understand them more. Then, in 1927, a man named Werner Heisenberg coined what we now know as the Heisenberg uncertainty principle. So we named it after him. Okay. We detect electrons by firing photons at them. Okay, so we can tell that an electron is in a location because a photon runs into it. This poses a problem, though, because when we detect an electron with a photon, it knocks that electron off course. Okay, so that would be like me putting you in an empty room with a bunch of balloons. Okay, so imagine like little water balloon-sized balloons, all inflated, and I blindfolded you, and I said, go and tell me where the balloons are. Okay, well, you're only going to know you found a balloon if you run into the balloon, and by running into it, you will have moved it from where I originally put it, right? So you would only be able to tell me, it was in the right corner of the room, but I can't pinpoint on a grid exactly where it was because now I have moved it by running into it. We run into the same problem with electrons because we detect them by how we can't look at them because they're so tiny, so we can only tell where they are by essentially bumping into them with other objects, which in turn moves them. So Heisenberg's uncertainty principle says that it's impossible to determine simultaneously, which means at the same time, both the position and the velocity of an electron or any other similarly sized small particle. Okay? At the same time, or actually just slightly before, that Werner Heisenberg was discovering this, Erwin Schrödinger was developing an equation that treated electrons as waves when they are in an atom. And he was able to come up with a way to mathematically calculate their energies because, as we know, if they're acting like waves, then they should have an energy associated with them. Okay? So if you remember, there were energy levels associated with the orbits of the electrons in Bohr's model, but they didn't fully understand why they had those energies or why they didn't run out of energy, and it's because we weren't treating them as waves. And now we are, so we can calculate their energy levels, okay? And these two principles together, so Schrödinger's equation and Heisenberg's uncertainty principle, formed the foundation for what we now know as quantum theory. And it's the modern theory of the atom. So it's our current best understanding of the structure of the atom. And it's mathematical. Quantum theory describes mathematically the wave properties of electrons and other similar very small particles. So, orbitals, different than an orbit from Bohr's model, because orbitals show locations where you are most likely to find an electron. If you remember, Bohr's orbits said this is the path that an electron will be in. It will be in this place and it will be orbiting the nucleus. Okay? Well, we now understand that we can't be that specific about it, because we can't measure the location of this electron without messing with it. And by observing it, we change the outcome. So, we can only say this is a general area where you are more likely to find an electron than another area. Okay, so we can say in this area, we very rarely find electrons. In this area, we find them pretty often. Okay? We can't say it's specifically in this exact location. We can only say, hereabouts is where we would find it. Okay? And we can say you're more likely to find it here than somewhere else. We can say that. Okay? We quantified the location of an electron in a specific orbital using a set of quantum numbers. So as I was describing to Irene before we started class today, it's helpful, at least to me, to think about these as coordinates or directions to specifically identify an electron. So like you would have a set of XY coordinates for a point on a map, you have a set of 4 quantum numbers to tell you which electron in an atom you're talking about. Starting with the principal quantum number. The principal quantum number is represented with a lowercase n, and it tells you the main energy level that that electron is occupying. So it will tell you, is it in the first, the second, the third, and so on. Okay. N can be any positive number. So from 1 on up, as long as it's positive, it can be that number. And it should be a whole number. Okay? The larger the value of n is, the higher the energy of the electron, and the greater distance between the nucleus of the atom and that electron. So as we go up energy levels, we're getting more energy and we're moving farther away from the nucleus. Okay? More than one electron can have the same n value. Okay? There can be more than one electron in each energy level. How many exactly is determined by the number of orbitals in that energy level. Okay? And you can find the number of orbitals in a shell by squaring your n value. So for the very first energy level, 1 squared is 1, which means there will only be 1 orbital in that energy level. Sometimes we like to call these energy levels shells. Okay? So think of them as essentially nesting dolls. Your 1n shell is inside your 2n shell, is inside your 3n shell, and so on.
What's the total number of orbitals? Like, what are orbitals?
Orbitals is, so each orbital contains 2 electrons.
Okay.
So it's a space where you are more likely to find electrons than not, and there's 2 maximum per orbital. Doesn't always mean there are 2 in that orbital, but there's a maximum of 2.
So there's electrons in orbitals and orbitals in shells?
Yes.
Okay. And there's 2 orbitals max in an orbital, but there can be a different number in shells?
Right. So each shell can contain a different number of orbitals. Each orbital can only contain 2 electrons. For example, in the first energy level, we just said there's only 1 orbital, right? So that's the orbital that hydrogen's single electron is in. Okay? Helium has 2 electrons. Both of them are in that first orbital. Once we move beyond that, since there are no more orbitals left in the first shell, we move up a shell and start filling orbitals in the next energy level. And that's where lithium starts putting its orbital or its electrons. So the first energy level, because the total number of orbitals is equal to n squared, only has 1. In the second energy level, there will be 4 orbitals. Yes?
Is there a way for you to draw that out?
There is, however, as we are about to discover, orbitals are not all the same shape and they get tricky and weird to draw. There are pictures of it in your book, though, if you want to look at them.
If you have the 4 orbitals in a shell, are they maxed out? Do they have to be 2 in an orbital to move on to another orbital? Or can
Yes.
They be 1?
Well, we're going to talk about that,
Okay.
but that's for a later time. They can fill... We'll get to it later. It's more. It gets more complicated. The order in which they fill, we will talk about in the next lesson.
Okay.
For now, just know we fill inside to out. And when we run out of orbitals in one energy level, we move to the next one. That energy level does have to be complete, usually, before we move up to the next energy level.
But the order of which that
Yeah.
energy... Okay.
It's a little more complicated than that. I have oversimplified it a little bit, but we will get to that. Okay. Second quantum number is the angular momentum quantum number. We represent this with the lowercase letter L. It's usually written in cursive because lowercase L can look like other letters, so we write it in cursive to differentiate it. Okay. For all except the very first energy level where we know there's only one orbital, there are sublevels, right? We said there's 4 orbitals in the second energy level, and they are divided into 2 different sublevels. Okay? Orbitals in these sublevels are shaped differently. Okay? L can be any number from 0 to n minus 1. So if your n value is equal to 4, then your L value can be either 0, 1, 2, or 3, because 4 minus 1 is 3. So you can have any number from 0 to 3. Okay? L is going to describe that whatever the value of L is, 0, 1, 2, or 3, is going to describe to you the shape of the orbital. So if L is equal to 0, what you are describing is the s orbital, and there's only one s orbital for every energy level. So the orbital that's in the first energy level is an s orbital. S orbitals are spherical. They're like a ball. Okay? If your L value is equal to 1, you're describing a p orbital. In every energy level that can contain p orbitals, there will be 3 p orbitals. So remember how we said the second energy level has 4 orbitals? They have 1 s orbital and then 3 p orbitals. If you would like to look at the shape of the p orbitals, they are in your book. Okay. If L is equal to 2, we're describing a d orbital, and if an energy level is capable of holding d orbitals, it will have 5 of them. Okay. So the third energy level can have a total of 9 orbitals, because 3 squared is 9. 1 will be an s orbital, 3 will be p orbitals, and then 5 will be d orbitals.
So if you get to the d orbital level, you have a total of 3 s orbitals, like they stack, or is there just...
So each energy level has its own s orbital. So by the time you get to the third energy level, you'll be in your third s orbital.
Okay.
Yes. Okay. And if your L value is equal to 3, you are describing an f orbital, and there are 7 f orbitals for every energy level that can hold them. Okay. We'll talk about how we come up with those numbers later. So if I'm saying to you that I'm looking at the 2p orbital, then I'm talking about one of those 3 p-shaped orbitals that exists in the second main energy level. Okay? So 2 is your n value, p is your L value, so I'm telling you I'm looking at one of the p orbitals in the second energy level. How I tell you which one of those I'm looking at is the third quantum number, which is the magnetic quantum number, m sub L. Okay? This indicates the orientation of the orbital around the nucleus. Essentially, it tells me which one of those p orbitals or d orbitals or f orbitals I'm looking at. Your value for m sub L can be anything from whatever your L value is as a negative number to whatever your L value is as a positive number. So that means if my L value is 3, I can have -3, -2, -1, 0, 1, 2, or 3 as my m sub L value, which is why there are 7 f orbitals. So this is just my way of indicating to you which specific f orbital I'm talking about. I'm talking about the -3 f orbital. Okay? So I would tell you, like, we'll get to an example at the end, actually. Okay? The last number is much easier than all of these. It can only have 2 values. It's very simple, and it's the spin quantum number. It can have a value of either +1/2 or -1/2. Okay? This is indicating the spin state of the electron in an orbital. Is it spinning up or spinning down? Okay? Remember, there's only 2 electrons per orbital, so the spin number identifies exactly which one you're talking about in that orbital. So n tells me what energy level I'm in, then L tells me which type of orbital I'm in, sublevel. M sub L tells me which of those I'm looking at, and then spin tells me which electron spin up or spin down am I looking at.
And there's always going to be one that spins up and one that spins down if there's 2?
Yes.
Okay.
They will not, you cannot have 2 of them be identical. One of them will always spin up and one will always spin down. So, as an example, if I tell you that I am looking at the n equals 1 as my principal quantum number, that says I'm in the first energy level, which means that there's no value for L that I can have other than 0, because remember the value for L is 0 to n minus 1, which in this case would be 0, so my only option is 0, which also means, coincidentally, that my only option for m sub L is also 0. All that tells me is that I'm in the first energy level, and I am in the s orbital, and since there's only one, since I'm in the s orbital, there's only one of those, so there's not an option for m sub L to be a different one of the orbitals, because there's only one, right?
What did L tell you again? L told you.
L tells you the shape of the orbital.
Okay. And then M told you
Which orbital, right? So if L was 1, then m sub L would tell me which one of the 3p orbitals I'm in. And then spin tells me which electron, the one spinning up or the one spinning down. So this is the first main energy level, which is a spherical s orbital. It can hold a maximum of 2 electrons, and then depending on the spin, I know which electron I'm talking about. So it's like a road map to find your electron, is what these quantum numbers are.
Can you explain the photo real quick?
Yeah, so it's just showing you, we have an X, Y, Z axis to show you that this is a 3-dimensional sphere, and that it's a spherical orbital that's got 2 electrons in it. That's all it is. I know it looks weird with the X, Y, and Z coming off of it, but those are just there so that you understand that this is a ball, not a circle. It's a sphere. Okay?
The orbital's a sphere? Or
Yes. The orbital is a sphere. So they're saying within this spherical zone, you are more likely to find an electron. Okay? So it's not saying that the entire sphere is an electron or that the entire sphere is completely full of electrons. It's saying there are 2 electrons in here, and within this area, your probability of finding one of them is higher.
Okay.
Yes.
I'm gonna be honest, I can't picture this in my mind.
Tomorrow, we are going to try using some balloons to make this a little more physical, because I understand that this is a very conceptual thing that is very difficult to understand.